Hello, welcome friends. Myself, Dr. Jayakrishnan. I am a faculty in the Department of Physics in MES College, Ponnani, Malappuram district. And here I am presenting my topic as a participant in the BSS EKM Astronomy Workshop. And in today's session, I will be presenting my talk on the celestial coordinate system. Here I will introduce what is celestial coordinate system and how this is applied in astronomy as a measuring tool, as a observing tool of different heavenly objects. Okay, basically we'll be talking about celestial coordinate systems, different types of celestial coordinate system, and what are the naming done in coordinate systems, and what are the origin taken, what are the references taken, and with the references how coordinates are measured, and other matters. So, and as you know, coordinates are used to locate objects or points. In ordinary mathematics, we talk about coordinate system, where coordinate systems are usually used to designate a point or an object in a 2D or 3D space. Okay, so usual thing, either in 2D plane or in a 3D space also. Using a three-dimensional coordinate system, we can represent a point in space also. So when we come to astronomy, where also we deal with heavenly objects. So position of heavenly objects can also be defined or referred by using such coordinate systems. So that is known as celestial coordinates. Okay. So for tracking the motion of objects, it may be a satellite, it may be a planet, it may be an asteroid or comet or anything like that. So in order to track them, we need some unique coordinate system. Only then we can transfer the observation to some other person. Or if you want to record them, the coordinates or the presence of an object, we need some reference frame. So essentially, these are reference frames, okay, used to locate objects in space. So, these coordinate systems are actually assumed or imagined within a large spherical space. Okay, so we need some space to imagine a reference system or a coordinate system. If you want to imagine them, we need a space. That space here is taken as a spherical space. So that imaginary spherical space is called a celestial space. So let us see a few more details of a celestial space. Okay. So for that, consider the figure 1. Here we can see the Earth. Okay, Earth is revolving. And suppose you are standing on Earth and observing the sky. What you usually feel? You usually feel that all the objects in the sky, in the space, are pasted on some spherical surface. This is a usual feeling. It's an apparent feeling which every common man gets when we observe the sky. All objects are pasted or sticking on some surface. So that surface we can call as a celestial surface or a celestial sphere. Okay, so every object is felt to be located on a spherical sphere. Okay, here also you can see that in the figure 2, some shining objects you can see. So it's a visual artistic impression of the celestial sphere. At the center we have the Earth. Okay, Earth is here, and all other objects seems to be existing on a surface, a spherical surface. That spherical surface is called a celestial sphere. Okay. So all bright heavenly bodies are situated and far away from us, but all of us are. And all such objects appear to lie in the surface of a large sphere of infinite radius, whose center is at the observer's eye. Okay, here center is taken as the observer's eye. Every object seems to be on the surface. That apparent sphere or imaginary sphere is called celestial sphere. I hope you got some idea about the celestial sphere. It is imaginary, Still, this concept is very helpful in locating objects in the space. Okay. So without imagining the sphere, it's very difficult to locate them or refer them or to transfer your knowledge to somebody else. Okay. So that is why we have such a concept of celestial sphere. Okay. So now let us move on to the coordinate system. These different coordinate systems are there. From time immemorial, or you can say ancient times itself, people felt the need of assuming some coordinate system so that objects in the space can be located and referred very easily. Okay, so during the period of time, many such coordinate systems were evolved. Some of them were got obsolete or useless, so that were discarded, and some more modern system were developed. And now we have very advanced coordinate systems. And let us see a few among them. The first one is called horizon coordinate system. We will talk in detail about horizon coordinate system very soon. And the second one is called equatorial system. This is also a coordinate system. Every term has its own meaning. Its evolution we will talk in brief. And the third one is called ecliptic system or ecliptic coordinate system. And the fourth one is called the galactic system. This is much more advanced than the earlier three. And we have the latest one called the supergalactic system. Okay. These are the 5 major coordinate systems used to locate extraterrestrial objects. Okay. So out of which we will be in today's session, we will be interested to talk about the first 3 one. Okay. These are the major coordinate systems used to locate objects from the Earth. So we will be focusing on the first three systems today in today's topic. Okay. So come with the horizon based coordinate system. You have the idea of horizon. In Malayalam we call it Chakravalam or something like that. Suppose you are standing on the Earth. Suppose you are standing on a vast plain ground, and you look at faraway objects. What you feel? You usually feel that the surface is extended to infinity. Or you can have the same feeling when you are standing nearby a beach or a seaside, and you look at a faraway point. What you feel? You feel that the surface is matching with some celestial sphere. Surface is merging with the celestial sphere. Okay, at the far end. So that means the entire plane is felt to be joining with the celestial sphere at far away point. So that plane, the horizon plane intersect with the celestial sphere. So that plane is called horizon plane, and we can imagine a circle. That circle is called horizon circle. So our first coordinate system is based on this horizon plane. Okay. In the horizon plane, if you are standing, you can locate any star, and the star can be designated with some coordinate. So let us see how this is done. For that, you have a sphere here, celestial sphere. This is the celestial sphere, and your small tiny Earth is here. Okay, you can see tiny Earth is here, and you are here at that point, and you are looking at the star. So then, how origin is taken? Origin of this coordinate system is taken as the geographical north. Okay, geographical north. In the sphere, you can see this is north, and the angle you make an angular measurement. Okay, so here is your star. You can draw a meridian line to the celestial sphere. A meridian line, a meridian line like this on the surface, celestial surface. So that line will intersect the horizon plane at some point. Okay. So here, suppose you mark this point as X. So this meridian intersect the horizon plane at some point. The angle measured from the geographical north to this point, geographical north to this point, that is the first angle. Okay, first angle. Okay, you can call it some inclination or horizon angle or something called azimuth angle. That the astronomers' favorite name is azimuth angle. Okay, so this azimuth angle is one of the coordinates. Again, in order to reach the star, you have to move like this in the meridian plane also. So that angle is called the altitude angle. Altitude. Okay. So altitude is the second coordinate. So this way, using azimuth angle or azimuth and altitude angle or altitude, you can locate the star in the sky. Okay. So this is the method by which star is located in the horizon-based coordinate system. Understand? I hope the idea is clear. Let's sum up once again what are done in horizon system. Here, geographic north is taken as the origin of the coordinate system. Origin. Your measurement begins from geographic north. Okay, measurement starts. So first thing, and secondly, azimuth angle is measured on the horizon plane. So this is the horizon plane, as you know, and your angular measurement is done in this plane. So that angle is azimuth angle, designated as the theta. And the second angle is called altitude angle, and that is measured in the meridian plane. Okay, in the figure you can see this is the meridian plane or altitude angle. So two angles measured. Angles are usually measured in degrees. You can also measure degree can be again subdivided into minutes. Minutes can be again subdivided into seconds. So for minute measurements, you can use seconds also. Okay, so that is usually required. So angular measurement done in degrees, minutes, and seconds. Okay, so that will help us to make measurements more accurate and precise. Okay? So now let us come to the second coordinate system, that is called equatorial coordinate system. Okay, where alpha and delta are the coordinates. Let us see what is this alpha and delta. So what is equatorial actually? Equatorial plane that is coming out of the word equator. You know, the longest till the latitude on the earth is called equator. Okay, this is our earth as you see, and there is an equator at the middle. If you imagine a extended surface parallel to the equator, this is the extended surface, the blue surface that you can see. This is the extended surface parallel to the equator. And in the figure you can see that this extended surface intersects with the celestial sphere. And this is our celestial sphere, and this extended surface intersects the celestial sphere. So that intersecting plane gives you a circle. Okay, this circle is called a celestial equator. This circle is called celestial equator, and this plane is the equatorial plane. So we need this plane here to make the measurement. Our coordinate system. In the previous topic, we took the horizon plane as a reference plane. We had a plane there, that was the horizon plane. Similarly, here the plane is the equatorial plane, or we can say celestial equatorial plane. Okay, this is that, and that is required for our measurement, first plane. And in order to make an origin, we need an origin also. Our measurement should start from the origin. How that origin is taken? Origin is taken as the vernal equinox point. So you know what is a vernal equinox point? How do we get a vernal equinox point? You can imagine two planes. One is the equatorial plane. One is the ecliptic plane. Okay, two planes are there. One is the equatorial plane. One is the ecliptic plane. Then question arises: what is an ecliptic plane? Okay, ecliptic plane we can easily find out. How do we find the ecliptic plane? Ecliptic plane is that plane in which Earth moves around the Sun. From the figure you can see this graphics, you can see that equatorial plane and the ecliptic plane are not same. So equatorial plane is shown in the green dots, whereas the equatorial plane and the ecliptic plane is shown with this dashed lines. Okay, they are not parallel, and instead they intersect. Okay, so you get the two intersecting points. The ecliptic circle and the equatorial circle intersect at 2 points. So we get two points. The first intersecting point we call as vernal equinox, and the second intersecting point we call as autumnal equinox. The first intersecting point is our side, the front side, And at vernal equinox, what happens? Sun will be exactly top of the equator, and we have equal day and night, and it usually happens at 24th March. And on the other side, we have the autumnal equinox. Again, the sun comes on the top of the equator, and again we get the equal day and night. So these are all well known to us. We are more concerned here with the vernal equinox point. Okay, vernal equinox point is here. That is taken as the origin of the equatorial system. Okay, origin where we start our measurements. Okay, so measurement is taken from vernal equinox point along the equatorial plane. So this is the equatorial plane. So let us see how this is done. We have the vernal equinox point shown in the figure and autumnal equinox point. And in equatorial system, we have the vernal equinox point as the origin, and the measurement is taken along the equatorial plane. So this is the equatorial plane. So two things are there. One is the measurement along the plane. Suppose star is here, you can draw a meridian again. The meridian will intersect the equatorial plane at some point. The angle is subtended by the intersection from the origin. That is called the ascension. The angle is denoted as alpha. And you have the second angle measured along the meridian plane from the intersecting point to the star. That is called the declination. That is denoted with delta. So ascension and declination are the two coordinates denoted with alpha and delta to mark the position of a celestial object. Okay. So let us sum up here. First thing is that vernal equinox is the origin of this coordinate system. As shown in the figure, vernal equinox is here. And second thing, ascension and declination are the two coordinates. Ascension is also called right ascension because we are moving rightward in order to make the measurement. So right ascension is usually used by astronomers, and the declination is the angle measured along the meridian plane. So that is shown here. The angular distance from the vernal equinox to the point where the meridian intersects with the celestial equator is called ascension, alpha. Okay, so angular distance between the star and the celestial equator is called declination. So these are the things to be discussed in the equatorial system, the second coordinate system, and usually both are marked on the figure. Okay, this is the declination and this is the ascension. I hope the idea is clear. And usually we know in measurements or in telescopic measurement, either you can use equatorial system or ecliptic system also. In many old models, even horizontal systems are also used. One can select appropriate system for their particular use. In many modern telescopes, many coordinate system will be embedded in the server. Appropriate selection can be done using hand-controlled remote. So that is what is shown here. By suitable selection, appropriate measurement can be done, and the suitable catalogs are available, published by different astronomical groups world over. Okay, and now let's move on to the third coordinate system, that is called ecliptic system. As I already mentioned, in ecliptic system, the reference plane that we have adopted is the ecliptic plane. As already mentioned, ecliptic plane is the plane in which the Earth moves around the Sun. Earth is actually moving around the Sun. So there is a plane, and the measurement is done along that plane. In the figure, you can see the red line, that is the ecliptic plane. And here also, the origin is taken as the vernal equinox point. Okay, your measurements start from vernal equinox. Just like taking north. Whenever you make measurement on the Earth's surface, we take north or geographical north as a reference point. In a similar way, in astronomical measurement, you start our measurement from vernal equinox point. That is well marked and well understood. The direction is well understood, and your measurements start from that. Or any telescope, any standard modern telescope are well embedded with the idea of vernal equinox direction. Its orientations are well known to or well recorded in any modern telescopes. Okay, so here this is the origin of an ecliptic system, and in order to make the measurement, we have the ecliptic plane here. Okay, Earth is here. Don't confuse that. This is the Earth. No, absolutely. At the center, a spot is there. That is the Earth, and this is the celestial sphere. Okay, and this is the vernal equinox point, and here measurement is done along the ecliptic plane. Okay, so this is the first one. This is called the celestial latitude. Okay, celestial latitude denoted with the theta. Okay, and again a meridian drawn through the star will intersect the ecliptic plane at some point. So this subtends an angle. So that angle is shown here as phi. Okay, that is called the celestial longitude. Okay, sorry, the celestial latitude. The first one is the celestial latitude, and the second one is the celestial longitude. So that is denoted with phi. Okay, so idea is clear. That's some of the idea here. Here also, the vernal equinox is the origin of the coordinate system. It's shown here. And the celestial longitude drawn to the star intersect the ecliptic point at some point. Okay, so that is shown here. And the angular distance measured from the origin is the equinox point, origin to the intersecting point, shown as L, along the ecliptic plane. This is called celestial longitude. So this is the celestial longitude denoted with theta. And we have the second coordinate. What is that? Celestial latitude. The angular distance measured from the intersecting point to the star is called the celestial latitude. So this way, celestial longitude and celestial latitude are the coordinates used in ecliptic coordinate system, and origin is taken from the vernal equinox. Okay, so hope the ideas are clear. And in modern telescopes, as I already mentioned, appropriate coordinate systems are well programmed. One can select a suitable coordinate system. Once you tune a particular heavenly object with a telescope, modern telescope have the feature that it can continuously track the motion of the heavenly object. Once an heavenly object is tracked and spotted, telescope will continuously monitor the movement of the object in the space. Okay, this way continuous motion or movement of the object can be properly studied. So such telescopes are available in the market today. One can use appropriate telescopes and do our astronomical observations very wonderfully. Okay, so these are some of the important points. So once again, let us recap the ideas. We studied about the different celestial coordinate systems. The first one was horizon system, the oldest one, and in which geographic north is taken as the origin, and the azimuth angle and altitude are the coordinates used to locate objects in the space. And the second coordinate system was equatorial coordinate system, in which vernal equinox is taken as the origin, and celestial equator plane is taken as the reference plane, and the ascension and the declination are the coordinates used to locate the objects. And the third system was the ecliptic system, taken on the ecliptic plane, in which again vernal equinox is the origin, and the longitude, celestial longitude and celestial longitude are the coordinates used to locate the points. Okay, so these are the main ideas that we studied in this short video session. So with these comments, let us conclude the session. I would like to express my deep gratitude to all the members of the fraternity, DSS CKM, Astronomical Society. Thanking you all once again.